Calculating the pH of strong bases is a little bit more complicated, and this tops out our Chapter 20 exploration. Strap in, this is quite tough, but with a bit of focus we can get through this together. We can calculate the pH of strong bases by taking advantage of a little bit of information that we have about water. You see, with all of these, they're dissolved in water. And it's actually the water that is responsible for donating some H+ that enables the pH of an alkali to be measured. On first thought, you would think that having any H+ ions in an alkali or a base would not be allowed because it would just surely cancel out straight away with the presence of OH- or some such thing. No, it's this, that the actual water it's dissolved in will continually provide a small amount of H+. There's always going to be H+ from the water component because water partially dissociates itself, forming H+ and OH-, even in strong alkali conditions. Now, if we look at this diagram here, we can see two water molecules, and of course what happens is one of the hydrogens from one water is actually separating from the oxygen and the hydrogen of that water molecule, forming H+ and OH-. But of course, the H+ doesn't float around by itself. We don't have protons roaming around inside water. The H+ gets looked after by a spectator molecule. In this case, it's an adjacent water molecule will take a third hydrogen, forming the hydronium ion, which is H3O+. Now, we don't have to include the hydronium. We can just call it H+, because it really doesn't play any other part. Now, what you can see here is in our language, our Bronsted-Lowry language of conjugate acids and base pairs, we can see that one of these water molecules has accepted another hydrogen, H+. And so therefore it has acted as a base, it has accepted. Whereas the other water molecule that has donated the H+ has acted as the acid in this situation. So water is simultaneously acting both as an acid and as a base, and this is only to be expected because when it dissociates it ends up with H+ ions, the acid component, and OH- ions, the alkali component. We can write out the dissociation of water as if it was a weak acid, and you can see here the H2O is in equilibrium with the H+ and the OH- ions, and because we can write it out this way, we can substitute it into the expression for the dissociation constant of acid, the Ka. And remembering that this was very similar to the equilibrium constant Kc, where you have the concentration of the products multiplied together on the top line divided by the concentration of the reactants on the bottom line. And that basically enabled you to see, is this reaction occurring to favour the production of the products or backwards to favour the production of the reactants? Well, we only have one reactant, it's water. So there's only one thing on the bottom line of this, and that is the concentration of the water. On the numerator line, we've got the concentration of the H+ ions that it produces and the concentration of the OH- that it produces in equal number. Now, luckily for water, the concentration is known and it's always the same. You see, the number of moles that fit into any particular unit volume is always going to be the same for liquid water. So if we take the concentration as the number of moles per unit volume, and we know that that would be the same as the number of moles, which is the sample mass divided by the molar mass, divided by the volume, which is the same as saying it's the sample mass times the volume divided by the molar mass. And so therefore we've got 1,000, which is the 1,000 grams, the mass of 1 decimeter, multiplied by 1 decimeter, and divided by the mass of 1 mole, which is 18 grams. And we get the concentration of water is equal to, and always equal to, 55.6 moles per decimeter cubed. Now, we can therefore write the above expression, We can multiply both sides by the concentration of the water. It moves the denominator to the left. So we have that the dissociation constant multiplied by the concentration of water is equal to the concentrations of the two ions multiplied together. Now this value is always going to be the same because the dissociation constant of water isn't going to change and neither is its starting concentration. So we know that the product of the concentration of H plus and OH minus always equal this same number, the ionic product of water it's called. And it has a value of 1 times 10 to the minus 4 moles squared dm to the minus 6. Now this ionic product of water sets the neutral point on our pH scale, and I'll show you why. You see, when we have H plus and OH minus produced, they're always produced in pairs because water molecules will always break into these two in equal numbers. It means that in terms of their pure number, we could represent the product of H plus ions and OH minus ions as simply numerically the same as taking the concentration of H plus ions multiplied by themselves. Because why multiplying by themselves? Because there's the same number of OH minus, and so therefore it's the same as multiplying it by anything that's the same number. OH minus and H plus have the same number. So it's equivalent to say that the concentration of H plus squared is equal to the concentration of H plus multiplied by the concentration of OH minus. And the concentration of H plus squared is equal to that value we found before, 1 times 10 to the minus 14. Now by taking the square root, we can say that the concentration of H plus ions in water is equal to 1 times 10 to the minus 7 moles per decimeter cubed. And now since the pH scale is just a measurement of how much or what concentration the H plus ions are at, we can put that into our familiar formula for the pH. And so minus log to the base 10 of 1 times 10 to the minus 7 gives us that the pH of water is 7. And so therefore, neutral point water is pH 7 on that scale. What this means, of course, is that even in a strong alkali, we will have some H plus remaining dissociated from the water itself, and in a strong acid, we will have some OH minus kicking around. It's important to remember that these two ions, the H plus and the OH minus that have come from the water, will always multiply to this 1 times 10 to the minus 14 value, the ionic product of water. Now, if we have a pH of 3, then what we know is that by putting that into the rearrangement of the formula, that pH equals minus log of the concentration of H plus, we know that 10 to the power of the negative pH will give us the concentration. And so 10 to the power of minus 3 will give us the concentration, is the concentration of the acid. But what we know is because we have the ionic product of water being 1 times 10 to the minus 14, is we can also go one step further and work out the concentration of the OH minus ion. Now here's a worked example that will show you how we do that. So imagining that we have a pH of 3.25, wants to know what is the concentrations of H plus and OH minus ions in this solution. Don't get wrapped up in, well, what acid is this? Why is this pure water or is this an acid? We're saying that this is something dissolved in water. So we don't have to think about what acid has been added to it at this stage. All we need to do is work out how many H plus ions there are and how many OH minus ions there are, and what the concentrations of these two would be. So the very first step is, from this pH, we want to work out the concentration of H plus ions. And that's simple to work out because the concentration is equal to 10 to the minus pH. 10 to the minus 3.25 gives us 5.62 times 10 to the minus 4 moles per decimeter cubed. Now, the final step is to work out what the concentration of the OH minus is. Now we know that the concentration of H plus multiplied by the concentration of OH minus has got to equal 1 times 10 to the minus 14. And so therefore, with our newly calculated concentration of H plus ions, we can do the simple formula of taking the ionic product of water, 1 times 10 to the minus 14, and dividing it by the concentration of H plus ions. So it becomes 1 times 10 to the minus 14 divided by 5.62 times 10 to the minus 4. And there you go, you can see the answer's calculated. The concentration of OH minus is also calculatable just by knowing these two things. If we know the concentration of H plus and we know the ionic product of water is always the same, then we can work out the concentration of OH minus. With this little bit of knowledge, calculating the pH of a strong base becomes quite straightforward. So imagine this, a strong base, it completely dissociates OH minus into solution. So for example, sodium hydroxide turns into sodium ions and hydroxide ions. Now, we can work out the pH of this calculation from just the concentration of the sodium hydroxide and the ionic product of water, Kw. So here is how the question sets itself out. It gives the concentration of the sodium hydroxide to start with, and it wants to know the pH at 25 degrees C. Because it is a strong base, it's going to have complete dissociation of the OH minus. So that means that the concentration of the NaOH to start with is the same as the concentration of the dissociated OH minus, because all of it has dissociated. That means we can set the OH minus in this example equal to 0.0750 moles per decimeter cubed. Now, using the method that we've just used, we could then find out what the concentration of H plus was in this solution. We know the ionic product of water is always equal to the product of the concentrations of H plus and OH minus, always equal to 1 times 10 to the minus 14. So, rearranging that, we could have the ionic product of water divided by the concentration of the OH minus would give us the concentration of H plus. So 1 times 10 to the minus 14 divided by 0.0750 would give us a concentration of H plus ions, very small, but measurable, 1.33 times 10 to the minus 30 moles per decimeter cubed. And now, through the straightforward pH formula minus log of the H plus will give us the pH, we can put in that very tiny value of the concentration of H plus, and we get a pH of 12.88. The trick of saying that, well, we know the concentration of OH minus because it's the same as the original concentration of the base doesn't work with weak bases, because not all of it, well, it won't be the same concentration because not all of it's dissociated. So we can't use that method for weak bases, but what we can do is a repeat of the methodology that we applied to weak acids. We could go through what we did in the previous presentation to work out the pH of a weak base. But just be aware that your methodology that we've just applied only works for a strong base.